I'm Suzanna Cuypers, a PhD student at the KU Leuven, and I'm the winner of the CLGE Young Surveyors contest. By showing you my project, I hope to motivate you to submit your project for the next competition. My research project, initiated by the industry, aims to test the feasibility of using drone imagery to monitor railways. I'll take you on a train ride into the future of automated and safe railway monitoring. Specifically, we focus on two planimetric measurements of the rails. First, we want to measure the gauge, which is the inner distance between the left and the right rail. And second, we want to know if the planimetric deviation from the as-designed rail positions is within the tolerance. Why not stick to traditional methods? Well, current methods employ rail trolleys with the measuring equipment on. These measurements have to be performed manually, and each rail has to be measured individually, which means the tracks need to be put out of service. This is of course dangerous and time-consuming. Therefore, switching to drone-based methods makes sense because they do not require track access and the processing can be performed automatically. This makes UAV-based methods safer and faster, hence this research project. We start with nadir imagery and ground control points measured every 25 meters along the track bed. The imagery is acquired with an RTK drone and 100 megapixel camera, resulting in a resolution of 1.17 millimeters. To develop the methodology, we pick out a study area with 4 ground control points. To tackle this problem, we devise a 4-step work plan. Step 1 is reprojecting the as-designed rails onto the imagery. In step 2, we test out several line detection algorithms. Then, in step 3, we filter out the detected lines. And finally, we visualize the results to obtain deviation maps. To align the imagery and obtain the transformation matrices, we use metashape. We undistort the imagery and add the 4 ground control points in order to improve the reprojecting of the as-designed rail lines. In the example, you see how these steps improve the localization of one of the ground control points. Now we can reproject the as-designed rail lines onto the undistorted imagery. We do this so that we can mask the irrelevant areas by making them black. This will help in focusing the line detection algorithms on the relevant areas. And we can also reduce data storage. Before we can perform line detection, we need to do one more thing, and that is to split the imagery into smaller tiles. Because the imagery is of very high resolution, the algorithms would take too long to run. Another advantage is that only tiles that contain a rail need to be processed. Line detection is a broad concept. There are several methods that we can employ, with each their own term. There's edge detection, where pixel contrasts are detected. There's line detection, where long, straight line segments are detected. And finally, there's segmentation, where all similar pixels are grouped together, and the boundaries between the pixel groups can be interpreted as edges. Here's a list of the methods that we will test. CANI is a very old but reliable edge detection method. HEAD and DEXINET are deep learning models. M-LSD is a deep learning line segment detector, and SUM is a recently released segmentation model developed by Meta AI. The 5 algorithms require different processing steps. We find that CANI gives reliable and fast results, but it is parameter dependent. Different lighting requires adjusting the parameters. SUM is also not suitable as it takes up to 1 minute for just one image tile. It's unrealistic to perform this for the entire study area. Deep learning algorithms HEAD and M-LSD are better, they are faster, and do not have parameters that need to be adjusted for each image. However, both algorithms generate a lot of overlapping lines, which makes it unclear where the rail edge is exactly located. That leaves us with DEXINET. Out of the tested algorithms, this is the best option for this application. It gives many short lines, but without overlap, and the edges are detected. Although it requires many processing steps, the algorithm runs really fast. When we look at one example with cables abstracting the view, we can see that HEAD and M-LSD indeed generate a lot of lines, all next to each other, which is why the lines look thicker. DEXINET gives a lot of short lines, but both edges are detected. The drawback of masking the irrelevant areas around the rails is that the edge of the mask also results in a detected line. However, we can filter out false positives based on several mathematical conditions. Then we pair up the left and the right rail to measure the gauge. Finally, we reproject all the detected lines onto the larger image, and using color-coded maps, we can visualize whether the rails are within acceptable tolerance or not. For example, this gauge map shows the distance between the left and the right rails, and green indicates the standard gauge. We can also verify if the rails deviate from the as-designed rail positions, but as long as the gauge is safe, deviation from as-designed plan comes second. In this area, the rails deviate up to 3 centimeters from the planned position. To conclude, we have devised a semi-automatic workflow to perform planimetric measurements of rails, and we found that line detection with deep learning algorithm DexyNet gave the best results. However, this workflow has a weakness, and that is its dependence on ground sampling distance and the accuracy of the ground control points. Our work was presented at the ISPR's Geospatial Week in Egypt, and we are awaiting publication. Next year, we take this project to the next level, which is to incorporate the altitude measurement of the rails. Thank you so much for your attention, and I hope to see your project at the CLGE Young Surveyors Contest next year. Good luck!